Welcome to Math 106, Chapter 2.1, where we are talking about describing graphs of functions. Now, there are 6 important categories when describing a graph, which are listed down here below. So first are the intervals in which your function is increasing or decreasing, which will provide us with the relative maximum or the relative minimum. They're using the word relative. This is interchangeable with the word local, which is the word that I use. It just depends on if you kind of use the SATs or ACTs, they had some different vocabulary, and that's kind of how it's perceived here. Now, number 2, the maximum or minimum values. These are your Y values here. So we're interested in the Y values. When we're talking about the interval, however, the interval, we're looking at your X values, because your X values are independent. They're doing pretty much whatever they want. So therefore, we're looking at your domain. Whereas your minimum and maximum values, we're talking about your Y values at that particular coordinate. Now we want to do the intervals in which the function is concave up or concave down, along with any sort of inflection points. And we'll talk about those here in a moment. Any sort of X and Y intercepts. Now we do want these to be in a coordinate, any sort of undefined points, and any asymptotes. So now let's take a look at some of your graphs. Now we want to determine, is your function going to be increasing or decreasing? And then as a result, will we have any interesting values here? So you'll notice that for the graph here, right, notice that at your point C, we are starting to go up. And looking at your increasing, notice that if you start to draw some slopes, right? Notice that all of your little miniature slopes here, are they positive, negative, or 0 or undefined? Well, all of these little miniature slopes, these are all increasing. All increasing lines. These are like little miniature lines. Therefore, M is positive. We are going to be increasing on a particular interval. But notice as that you are increasing, right? You start off really quick and then you start to slow down until you eventually get to a horizontal line, which I think I have here pretty soon, where we're talking about a horizontal line here in a moment. But notice that we are increasing over time. Now, the opposite is true down here. If we were to draw a few values down here, a few little lines, right? The majority of this interval, right? Because you have now a negative slope, less than 0 negative slope, these are going to be decreasing. And lastly, at C value, if we were to just take C for what it is, right? Down below, what would your slope of this horizontal line be? Well, your slope would be equal to 0, right? Horizontal lines have a slope of 0 because it's really their y-intercept. So Y equals at that particular intercept. So all in all, when we are at a local or relative maximum and minimum, we will be seeing this slope of 0. So when we talk about your maxes and mins, all right, I just said relative and local, those words are interchangeable. So a relative and local max or min, which is also called an extremum or an extrema of a function, is a point at which the graph changes in direction. So for example, right, could you draw a quick graph that has a minimum? Well, the best looking graph right here would probably be some sort of a parabola, a quadratic function, where we can locate your minimum at being the very lowest point here. This is and I should be specific, this is a local or relative minimum. So we know it's a minimum here because it's your lowest point, where again, your line here, your slope at this point is equal to 0. And we talked about there being a change in direction. So to the right-hand side, what is your graph doing overall? Well, on your right-hand side, if we were to draw a series of lines, right, notice that what would your slope be on this side? So your slope here on this side is less than 0. It's a negative slope. Therefore, we must be decreasing all the way until we get to your minimum value. So we are decreasing to the left. Whereas on the opposite side, on the right-hand side, notice that we then change direction as we go. If we were to, again, draw some miniature lines here, notice that your slope here, in general, is going to be increasing. These are positive lines. So we have a positive slope here. So therefore, on the right-hand side of your minimum, we are going to be increasing. Now, at your local minimum here, we are no longer increasing, nor are we decreasing, because your slope is 0. We are neither increasing nor decreasing. It's kind of like we are starting to pivot, right? We're moving, we decided that we're walking, let's say we're walking towards an ice cream parlor, right? We can see it, we're right at the door, and then all of a sudden we start to change our mind. In which case we're going to pivot away from the door, right? We were moving in that one forward direction. And then as we're pivoting, we're not really going towards the door, but our intention is to head backwards in the opposite direction. So therefore, this is kind of a pivotal point. We're just moving in a different direction. We're no longer falling, but in case we're rising. Or we're no longer going forward, we're deciding to therefore go backwards. And we can always change our mind later and then we can have a different circumstance, but think about it in that way. Now, that's just for a local minimum. Let's draw it again if we were to do a maximum. So here we have the opposite. Let's label your maximum here. So we have a local max or a relative max, which again here, if we were to draw your line here at your slope here is equal to 0, which we said is really your turning point, right? We're changing in a direction. So therefore, we are neither increasing nor decreasing. Now let's take a look at your function again. So what's happening on the right-hand side of your graph? Or sorry, the left-hand side. Let's do left first because we typically go left to right. Well, if we draw a series of little lines, you'll notice that your slope overall here is greater than 0. It's a positive slope. Therefore, we must be increasing. So we're going up on one side, and then on the other side, if we were to draw it one more time, notice that all of these lines are downward facing. Therefore, your slope is negative. Therefore, we are decreasing. We're going down. And on the other side, if we were to do it over, this is down, and then we change to up. So now at your local relative maxes and mins, right? This is just one graph, but our graphs might not look this nice and uniform. We could have lots of ups and downs, right? In this one, if I just drew it really quickly, I have 1, 2, 3, right? Local or maximum, or local or relative max or mins, right? These are just particular extrema of your function. However, when we talk about an absolute max or min of the function is the largest or the smallest, value of the function, assuming on its domain. So if I were to draw something real quick, let's say I redrew that graph from earlier, something like this. Can you pick out its local max and min as well as its absolute max and min? Well, its relative or local max and min, we can just kind of put right here. We have a maximum here. I'll say local max. I have a local min here. I also have a local max here. Now at this particular point here, right, we are still considered a local maximum, just like here. It is a high point on your graph. Now, is this also the highest point that you can ever get on this particular graph? Yes, so this point here, the way that it's drawn can also be not just a local maximum, but it's also considered an absolute. So this can double as an absolute and a local. Now this one cannot also be an absolute because you'll notice that while it is a high point, it is not the highest. This portion is a lot higher than the other. Now what about your local min? Would this one be considered your absolute minimum? No, this one actually is not considered your absolute minimum because down here, as your graph is pointing downwards with arrows, it's suggesting that these values will continue to get more and more negative, a lot smaller than this minimum value here. So we have an absolute minimum at negative infinity, and we know that it's in negative infinity because that is where this is implied. And you'll notice that it goes the same here. It's going down, so this minimum is the same as this one. And you'll notice that it's not always going to be the case if this continued to go upwards, right? This would no longer, or this would still be a local min. This would no longer be an absolute maximum because this graph would continue to go up. So it really just depends on the shape of your graph. Now let's talk about concavity. So this is just in reference to now, is it increasing or decreasing? We talked about these minimum and maximum values. When keep in mind, if it's just talking about a value itself, when we look at your local max or min, we're really referring to the y coordinate of that particular point. Now let's talk about concavity. It says, a function is considered concave up at that particular x value, so when x is a, if there's an open interval on the x-axis containing a, that should be in quotes, containing a, throughout which the graph of the f of x, so throughout the graph, lies above the tangent line. So as long as your graph is above the tangent line, if we were to draw it, above the tangent line, it is considered concave up. And real emphasis on the above. So you'll notice that in this one, right? If we were just given a quick graph here, that one in blue, sorry, it's a little fuzzy. When you draw your tangent line, you'll see these in black right here. If your tangent line, right, if your graph is above the tangent line, notice that when it's stacked, this graph portion here in blue, as long as it's found above that black line, we're going to be considered concave up. And you'll notice that down here as well, this line in black, that's your tangent line. And you have your graph here, and it's also above that, that graph or that tangent line. This is considered up, and that goes for all of these. Even if I were to draw another one, notice that if I were to stack, your graph here is still above your tangent line. So therefore, these are all considered up. So equivocally, it is also concave up if the slope of the graph increases as we move from left to right. So as we're going to be, and we typically looked left to right. So if we're increasing, notice that your tangent line here is a little bit lower and then it's getting bigger and bigger. So if we're moving left to right and it's going to be increasing, then we also have a concave up graph. Now, the idea is very similar when we look at its opposite. If we are concave down, instead of the tangent line being above the tangent line, or instead of the graph being above, the graph is now below your tangent line. From left to right. So you can now see the reverse. You'll see your tangent line here in black. And then everything in blue. This is your graph portion here. Notice that it's below that tangent line. And what I'm kind of doing is I'm actually showing you the concavity. If this graph were just very singular, notice that it's taking on this sort of N shape. Whereas the other one, if we were to draw a quicker picture, which maybe I do it in a different color, it kind of bounces off that tangent line. And you see it can kind of form the word up. Whereas this one, if it were to bounce off your tangent line, let's see, where's my tangent line? My tangent line here, it kind of forms the word down, where this is now the N of the word down. So that's kind of your concavity. Just draw a quick tangent line, and maybe you draw a few more and kind of determine where the graph is, and then kind of make this little concavity to figure out where are we? Are we going to be up or down? Now keep in mind, as we're moving left to right as well, if your slope starts to decrease, the slope of your tangent line, notice that the one in black, we started off really, we're increasing, and then we start to slowly decrease as we move from left to right. That also suggests going concave down. Now, when we want to identify an inflection point, it is a point on your graph of the function at which the function is continuous and at which the graph changes from concave up to concave down, or vice versa. So there is a switch in a reflection or an inflection point. Sorry, there's a switch between your direction. So let's take a look and see what these inflection points shown right here have in common. So notice that your tangent line is in black here. So if I were to highlight that they were in black, maybe I thicken that up a little bit. What are all of these points? These are considered your inflection points doing at that particular point. So these are all inflection points right there. So graphically, we can see that these inflection points, right, they end up going right through your tangent line. So they cross your tangent line, which typically we don't see any sort of crossing of your tangent line, right? They are typically either stacked below or above, and they're touching in that one particular spot. Ours, for your inflection point, it's crossing straight through that particular point. That is how you can identify your inflection point. So it crosses its tangent line. And you'll notice that when we talk about the change in concavity, right? It said we can go from from up to down. So your concavity here, it went from up to then now it's reverse going down. Because this then suggests that on this side it's down and on this side it's up. And then the reverse, it went down here. And then all of a sudden it switched to going up. So this side was up, this side was down, this side was up, and then on the other side was down. But notice that third case, right? We went from going up to then continuing. This one is now going down. Inflection point, we definitely want to make that an emphasis that it's either up to down or down to up. And you'll notice that we have these three cases here, and they can look very different based on where they are. But notice that you still have an inflection point right here in this third case. It is a pretty special case. Now, this third case is pretty special because what we're going to figure out is at this particular slope, where we have your slope here is equal to 0, right? This is also called a critical point. So your inflection point can be equal to a critical point. So just be aware the inflection point can also be a critical point at times. Not always is that the case, but there are, when we go to graph it later on in this chapter, that you might see the inflection point come up as the same critical point. So now let's go ahead and look at example 1. So use the graph below to answer your questions. So part A says find the intervals where the graph is increasing. Discuss the concavity. B is decreasing. Again, discuss concavity. C, find any sort of inflection points. And D, find any relative maxes and mins. So let's see if you can pause the video and see if you can try these out. So let's start with A. We want to know where the graph is increasing. So we said to determine if the graph is increasing, if we were to just draw a couple of these values here, right? A couple of these, let's say these tangent lines. In order for our tangent line to touch, right? Let's say at this point, we'd have to be above that graph. In other words, your graph, right, concavity-wise, should be concave down. So overall, if we were to make that tangent line where we're touching your graph just once, the overall graph here should be concave down. Now, does that concavity stay put at this particular value here at x is equal to 3? Notice that the general shape here, they've already given us the tangent line. So your concavity is seen, therefore, below. So we are, in fact, decreasing. And we can suggest that all of these would be, in fact, concave down through these intervals because there's no change in that concavity that we can see. So therefore, we are decreasing. And let's assume that there are arrows off this page. So we're increasing this tangent line that we can see. These slopes that we've seen on your line are going to be increasing until they get to this particular point here. So we're increasing from negative infinity all the way to 3. Now at 3, right, when x is equal to 3, right, all of a sudden we've stopped moving. This is your turning point, right? We've now decided that we are going to move in an opposite direction. So if I were to draw another line again, this is now a negative line. So all of that starts to decrease, which means that this is being your pivot point. We're no longer increasing or decreasing, which means that we're going to use parentheses around this 3. So that is where your graph is increasing from that interval. Now, is there any other portion of your graph that looks to be like the slope starts to increase again? Well, if we were to draw more, they already have this one here. At what point do your lines start to increase once more? Well, your lines increase once more after when x is equal to 5. So from 5 and up. So we can use that by saying union 5 to infinity. And that is where just all of these little black lines, where are they positive and where are they negative? Now this is for increasing. If we were talking about concavity, let's take a look at that concavity. Well, we said, okay, well, these lines being above your graph or your graph line below, we can see that these little marks here are your concavity. So overall, we are decreasing on your interval, not decreasing. We have concave down all the way until what particular value? Well, all the way until we get to this inflection point right here. This is the inflection point where all of a sudden this tangent line crosses your graph. And now the act of crossing, notice that your tangent line, I drew it incorrectly over here because I was going a little too fast. Notice that your tangent line, in order to touch this graph appropriately, it now switches to being up. And therefore, as a result, the remainder of these graphs will also be concave up. Because notice that the tangent line here, if I were to draw them more accurately, would therefore be right underneath that. So concavity here, over the intervals, the concavity for your increasing, let's see how I wanted to say that, is down from negative infinity to not so much at 3, because at 3, we're still concave down, but at what point did it switch its concavity? Well, it switched its concavity at 4, which means that it's going to be neither increasing nor decreasing, or sorry, it's neither going to be concave up or down at this particular inflection point. So it was down at 4, and then it switches to up from 4 to infinity. So now where is the graph decreasing? So anywhere where you have a downward facing slope, so we have a slope which is horizontal, so that means it's equal to 0. So anything on the opposite side, notice that again, it's going to be decreasing. It's going to be decreasing over the interval between 3 to 5, non-including 3 and 5, because at 3 and 5, where your slope now is equal to 0, we're no longer decreasing. We're not moving. And again, your concavity, if I wanted to discuss concavity, it's now up from 4 to infinity. Your inflection point, we just talked about, it is the point in which your concavity switches its position or its direction. So we went from 4, 4, which is your inflection point. And we do not have any other inflection point because you notice that these are all down until we then switch these to up. And our graph continuing off the page, that is the only position in which we change from down to up or vice versa. Now, any sort of relative maxes and mins, this is where your slope of your tangent line is equal to 0. So that would be at your point. So let's see, a maximum, our max happens to be up here at 3, 5. And your minimum happens to be right here, 5, 3. If we're looking for the value, we're just going to be saying this is your y coordinate, the value at 5, or the value at 3. So again, to kind of recap, your inflection point is where there's a change in concavity. Need to spell that word one more time. There we go. Change in concavity is your inflection point. Relative or local maxes and mins are just extrema found within your graph. Increasing is where your lines are either positive or negative if we're decreasing. At zeros, this is where we do have any sort of max or min. These are called your critical values. Now, can you use the prompts from the above, so A through D, and describe this particular graph? So if we were to do the same from before, let's say that we are looking for your increasing interval, your decreasing interval, your concavity. We'll say up and down. We also were asking about maxes and mins and any sort of inflection points. So let's try and label those on your graph. So let's go ahead and see your increasing or decreasing. So if I were to draw really quick some lines here, just some tangent lines in order to touch your graph. I'm just going to draw a few. There we go. So what can we notice about, at the very least, increasing and decreasing intervals? So in our case, notice that all of these black lines to the left-hand side of your graph, these are all decreasing. Now they are starting to get less and less negative. So we are slowing down as far as your decreasing interval. So we went from 1 and we all of a sudden stopped decreasing when we were at 3, because at here, your slope here is equal to 0. This is your critical value here. You stop decreasing at 3. And you'll notice that because this 3 is in parentheses, notice that you're no longer moving. You're not increasing, you're not decreasing, you are not moving. So you're not increasing and you're not decreasing. Same thing in that it's showing that here. So now when are you starting to increase? Well, the second you pivot, the very next value, that could be at 3.0001, you then start to increase your slope. So you go from 3, non-inclusive, and it looks like we are still continuing to increase. Now we don't have much information. We're just going to assume that I think this is just going to continue because it doesn't have a solid line. So we'll just suggest that it keeps moving, but we're going to increase all the way to infinity. Now, do we have any max or min? We no longer have a maximum, or at least not a local maximum, but we do have a local minimum. Where is your local minimum? Well, you'll notice that I'll take just about any answer, but notice that it's just slightly under 1. So when we talk about this coordinate, we might be interested in the coordinate 3, comma, and then something close to 1. I think a previous class of mine had said 0.9, so we'll kind of stick with that. Or if they didn't ask for a coordinate but a value, we're looking at where your y value is at 0.9 or 0.9. Now let's talk about inflection point. Do we have an inflection point where we change in your concavity? Well, maybe before we get to this inflection point, we can actually talk about your concavity. So looking at your decreasing slope, and we said anytime that your slope starts off really negative and then starts to get less and less negative. So it's starting to therefore increase, right? We actually are going to be concave up, right? Concave up, concave up. And then all of a sudden at this particular value here, something happens. And then notice that as a result, your tangent lines are seen on the opposite side. Therefore, the overall action here, our inflection or our concavity starts to turn. We were up and now we are down. Therefore, we have an inflection point at the coordinate at about, let's see, 4, and we don't have much context. Let's say they're going up by, oh, these are going up by 1s. So this is about 4 and 1.5, rough estimate. So your inflection point here, 4 and 1.5. And therefore we can use this 4, right, the x value, to then determine your concavity interval. So we were facing up, starting at a solid dot at 1, all the way up until 4. So from 1 to 4. And 4 is non-inclusive. However, 1 is going to be inclusive because we are around that value where we are concave up. And you'll notice at 4, we start to switch, so we're neither. And then we go down from 4, and then the rest of our arc is down. Now, infinities, they never get brackets, they're always parentheses. Now, there is one other special feature. Well, two if we think about it, is that dotted line. It's there for a reason. Now, when we have dotted lines, these are actually called asymptotes. This happens to be a horizontal asymptote. So your asymptote here is at y is equal to 1, 2, 3. So your horizontal asymptote, typically asymptotes we cannot cross. However, you can cross a horizontal asymptote at times. This is when your x value is not going towards infinity. You'll notice that it's crossing here because your x value is not going towards infinity. However, as we continue, your x values over on the other hand, x goes to an infinity, right? It is going towards, in this case, positive. This one over here is going towards negative infinity. So it can have the potential of crossing a horizontal asymptote. However, it will never cross a vertical asymptote, that being an up and down line in which your graph cannot touch. So you do have another additional special feature. I'm going to push this inflection point up here. We have a horizontal asymptote at y is equal to 3. Now, do we have any sort of undefined points? We do not have any undefined points. These are undefined on your x value. This would be affecting your domain. We could see these, in which case it would be looking like a hole or a vertical asymptote. In which case we don't have any holes. A hole would be a giant gaping hole, kind of like a pothole in the middle of your graph where we cannot touch, or a horizontal or a vertical asymptote, again, another dotted line in which your domain can no longer handle. In which case we don't have either, so we can say none. Now let's have you guys try example 3, which is going to be a little pop quiz. So pause the video, see if you can do the following questions. So example 3 says, does the slope of the curve in the graph below increase or decrease as x is increasing? So as x is increasing, this is when x is going towards infinity, right? How we are getting bigger. What is happening to your overall slope? So if we were to draw your slope here, what is happening over time to those slopes for your tangent lines, right? Well, maybe if we were to assign this, maybe this is -8, and maybe this is -6. Maybe this is -2, or maybe -1. Maybe this is starting to get towards -0.5. What's happening with your slope, right? Well, we're going to get your slope is decreasing, overall it's decreasing, right? Well, you're decreasing in the form of it's starting to slow down. It's no longer being as quick, but yes, it is getting less and less negative, right? But overall, your slope is starting to go towards zero. At which point labeled below on your graph is the slope the least or the smallest? So if we were to draw some points through your graph here, let's see. There we go. So here being your tangent line. Maybe I redraw this one a little bit more. So which one is the least steep, I think is the way I can structure that question better. Well, that would be at your point 3, 3,2. So notice that these lines being pretty steep, right? These two are pretty steep, and this one is not nearly as increasing as fast. Now let's do 5. So choose the circles in which they apply. So it says, which labeled point is the function decreasing? So assuming that these are all kind of in reference to some sort of slope or concavity. So if we were to draw a series of slopes here, here we go. There we go. So if we were drawing some functions or some points where where are we decreasing? Well, we're decreasing, those black lines are decreasing at A and E. And at which point is where are we concave down? Well, if we were to, and maybe I need to make A look a little bit better. There we go. That's, oops. Still decreasing, but notice that it's below. So if I were to touch and bounce off, and maybe I do that for the majority. What is going on with your concavity? Well, concave down, it looks like we're going to be concave down at D, and I think that's it. And concave up, we're at A, B, and at, well, maybe not so much at E, but at F. Notice that I didn't say at E because C and E are actually something more impressive, right? What's going on at C and E? Well, C and E, it looks like we've went from a concave up to then a concave down, or a concave down to then a concave up. These are your inflection points. What about B and D? What are those called? This one is your minimum, and this is your maximum. These are called your critical points. And notice that at your critical points, you have a tangent line that is nice and flat where your slope is equal to 0. And your tangent line of the other two are crossing your function. So now if we're continuing, it says, which labeled points has the most negative slope or negative with the greatest magnitude? Well, would that be at A or would that be at E? Well, it kind of is up for interpretation. I would say A is probably a little more flat than E. So I would say E here. At which point is the graph increasing? So your slopes now, we don't want negative, we don't want zeros, we have to be going up. So that would be at C and F. and which one is the most positive. So your most positive one between them, I might need to redraw C. No, C is okay. Notice that C is going up a lot quicker. So our answer should be C. Now that should be our conclusion of that little quiz and kind of recapping what we have learned this section.